So I think there is a lot of great talks today has been covered the background of polariton. So I will just skip some of the details, right? But I do want to mention that the polaritons can couple light in free space to the surface, even inside about the materials. This greatly boosts the light and matter interaction with particles, like some particles in the electrons, phonons, and the excitons, right? And when it comes to the materials, and the 2D family has a lot of different kind of materials, so it can support different kind of polaritons. And more interesting is that you can just stick this kind of layer materials together, right? And to create the van der Waals materials, and to explore even more exotic hybrid polariton modes, okay? And here I just list some of the materials has been discovered to support great polariton materials last 12 years. Sorry, I can't list all the results because the field's advancing very quickly. So these materials comes different dimensions, energy bands, and crystal symmetries. And each of materials can even put their own unique properties to polaritons themselves. And so we're considering a simple case about 2D plasmas, and its dispersion can be mainly depends on the conductivity, right? And so because it's a 2D materials, the 2D conductivity is like a sheet optical conductivity. Sometimes you can just simplify this kind of character by multiplying the bulk conductivity with the material thickness. And if you consider some polar crystals or some insulators, you can just transform this kind of conductivity into the dielectric function if you want. And when it comes to the conductivity change with light frequency, and there are two models we usually use, the Jude model and the Lorentz model. Jude model handles like Fourier carriers, plasma polaritons. Lorentz model deals with like phonon polaritons, and many particles, okay? And if you consider the magnitude and the sign of the conductivity, you've got different kind of iso frequency contours about the polaritons, okay? And you may got some closed shapes like circles, ellipses, and you can even get some open curves like hyperbolic forms. The hyperbolic polariton are particularly interesting because it can squeeze light into the very tiny space and the wavelengths, right? And this can be very enhance the photonic state, and can be promising to some applications like super resolution lenses and even negative refraction. And also there are listed some of the key areas about exploration about the 2D plasma polaritons. I think a lot of speakers has been mentioned today, but I just list 3 of the key areas. First is the squash light by hundreds of times. It's like a highly confinement wavelength, right? The second, you can use the monolayers and also use the very strong dielectric substrate, like gold substrate, to create the image mode, right? And the second, you can tackle the lowering losses, right? And techniques like isotope enrichment and low temperature has helped us a lot, right? And the third one is to explore some exotic polariton modes, like hyperbolic mode, ghost mode, shear mode, colorization mode. Everyone speaks here today, and also topological polariton. Okay, so our research are mainly focused about manipulation, this kind of exotic polariton mode, and to trying to design and fabricate some photonic devices. Okay, let's talk about graphene first, right? And in the experiment, we just mechanically exfoliate the ultra-clean graphene onto a substrate. This substrate prefabricates some holes, and the graphene just covers these holes to create the suspended graphene, right? And you see, because they are precious, so it's like a suspended graphene bubble, and then we can get this kind of suspended graphene plasma with long propagation distance, right? And even you can, change the size or the shape about this holes on the substrate, to achieve tailored suspended graphene plasmas, like some standing waves or plasma cavities, right? And you do know that graphene is a hexagonal crystal, right? And so it implies isotopic, right? So, and very recent years, the hyperbolic polariton has been discovered in the boron nitride metal surface or some natural materials like MO3, right? So there is a straightforward idea that you can just put these two materials together, right, to create the van der Waals structure and to study some mode coupling, okay? And here's the case. So when it comes to the conductivity, you can just zoom up each of the materials, right? But you should consider some coefficient, okay? And here is the result, and you can see when you change the graphene Fermi energy and this isofrequency contours about this hybrid polaritons can be changed from opened hyperbolic curve to a closed elliptic curve, okay? This kind of change has been known as a topological transition about these polaritons. This has well been studied in the twisted MO3 system, right? But in our graphene and MO3 heterostructure, I think the biggest advantage is the tunability, right? So we can just continuously and dynamically to tune this kind of hybrid mode right at the spot, okay, into sample. So, and you can just feed with some electricity with the sample. You can get this exciting changes about this mode. And there are some simulations and the experimental results in the real space, right? You can see when we increase the graphene energy and this in the real space, how the electric distribution of these polarities can be changed, to the hyperbolic, and there are some colorization mode to the elliptical mode, okay? And so if you get this kind of changed, tunable topological polarities in the graphene and the MO3 heterostructure, so you're trying to design some photonic devices, right? So here is the first example we are trying to do. And you see in the experiment, we fabricated gold, silicon oxide, and gold implant sandwich substrate, right? And then we put the MO3 and the graphene on it, and this antenna to launch the polarities. And you see, because the significant difference about the dielectric function about the gold substrate and the silicon oxide, right? So the polarity mode on the two different kind of substrates are quite different. You see, this is a concave curve about this polariton. In the momentum space, right? This is a transformed wave vector, and this is a convex shape, okay? So when you launch the polariton at this area, and this elliptical mode can be changed in this different kind of area, and then you can get this kind of colorization mode because the wave vector, the pointing vector, is on the different direction, okay, right? So this is on the positive one, and this is on the negative one. And so here's a video. You can see how this device can work, right? And when the polariton has been launched by this kind of antenna and go through about these areas, and you can see this, we can get some like diffraction layers about this colorization mode. So finally, we can just use a 1.5 micrometer wide about this substrate length, to give this kind of diffraction layers about this implant length, right? So this is the first example. And here is another example that we use this kind of topological polariton to design some optical devices. So this is negative refraction. And also, we use the same materials like MO3 and the graphene, right? And also to do the van der Waals heterostructure. But they are just half of the MO3 has been covered by the graphene, right? So we also use the antenna to launch the hyperbolic polariton when it goes through at the interface. It's the graphene edge, okay, to the right part, and this is the topological part, and this mode can be changed, right? And so you can go to see this process in the momentum space, right? To the general snails now, and you can see that the wave vector can be just conserved parallel to the interface, right? This is this, but this is not to use in the perpendicular component. So when the wave vector goes through like normal refraction, but the wave vector, the pointing vector, goes through the opposite way of negative refraction. And here's the experiment, okay? And you see, I think first you put the antenna on the left, right, and you see this kind of negative refraction, and the hyperbolic wavefront has been shrunk at the right part, and finally focus themselves here, right? And after this, we remove this antenna and fabricate a new antenna on the right part, I mean the graphene part, and slip the structure design, okay? And you see the antenna launch the circle waves and also focus after go through this graphene boundary, right? And the focus but in a hyperbolic way, right? And here we, because go to some details, right? And here we run some simulations, and you can see how this kind of reversible negative refraction can be changed, right? And with the graphene, energy can be changed, okay? And so you may know that graphene is like atomic layer materials, right? And it also has the direct linear band energy. So this gives us the opportunity, to design some field effect transistors devices, to control this kind of optical transmission, right? And here is the design about this structure. And here you see the experimental result, right? And when we change the gate voltage, you can see that the third fridge and changes from the hyperbolic to a focus spot, right? And also you are analyzing the pointing wave vector. You can see that the pointing vector on the right part, I mean, after cross the edge, it's the refraction angle can be smoothly changed or shift from the positive direction to the negative refraction. This can be considered as a gate tunable normal refraction to a negative refraction, right? And when you consider the intensity at this focus spot, you can say it's enhanced by a magnitude, right? And here. So I think this morning a lot of people said about this twisted MO3, right? So at the last case, we use the graphene and the MO3 topological polaritons to do the negative refraction. So next, we are also trying to thinking, how can we use this twisted topological polaritons to do some optical devices? And so we doing this kind of stuff, okay? And at this experiment, you see that we first pick up one of slab of MO3, and we cut up this kind of material into different shapes and different angles, okay? And we put this slab onto another MO3 slab and to create this kind of devices. And you put the gold antenna here and to sight the hyperbolic polaritons to cross this twisted area. Because this twisted area has the topological polaritons, I think the speakers has mentioned this morning. So this propagation behavior about this polaritons in this area has been totally changed, right? And you can see this start from the hyperbolic way and continuously change to also like a negative refraction we just mentioned. But there are some degrees about the twisted degrees, right? And it's some asymmetry modes here. And this symmetry here is very similar to the shear hyperbolic mode, like has been found in beta gallium oxide, and this is also this is also comes from the off diagonal about the dielectric function tensor. Okay, and next we do some control experiments that we can just to make more micro strips to steering of polartons with different oriented macro ribbons. Okay, here we just put 1 micrometer here, and you see the hyperbolic polariton cross here, and this because the twisted topological polartons. Okay, and here they has created this kind of colorization mode, and the pointing vector, I mean the polariton light flow, just shift to the right, and after the polariton refracted to the other interface, and it goes through the hyperbolic propagate straight forward. Then we can optionally to put 2 ribbons here, right? But in the same orientation, and you can see the polariton can be just shift twice and in the same way. And then we can slip 2 ribbons, right? We can get this kind of meso-asymmetric relationship about these 2 ribbons, and you can see the polariton can be shifted to the right, then you can refract it back to the original incident propagation direction, okay, here. And if you put more ribbons here, right, and you can see that this hyperbolic polartons can be first split and then turn a corner and then merge it back to create this kind of clocking devices here, right? Because this is a defect that you can see that the polariton field cannot touch this area, and it can be like considered as clocking devices. And you can imagine that if we not put these 4 ribbons here, right, this light can just go through this kind of defect and can be happen some unwanted reflection or scattering. Okay, so this is the third device we just put. And to summarize, I think we are trying to design of find vast material and structures to manipulate our polartons. It's a different way, and we advance the instrument, but it goes to the materials design and structures. Okay, and we are trying to several possibilities. First, we're trying to the suspended graphene with long propagation distance, and we have the graphene and MO3 heat structure to support topological polartons. And then we use this kind of topological polariton to create some gate-tunable negative refraction. And at last, very recently, we developed this steering and clocking polariton devices. Okay. So look ahead, and we do the samples, right, and material and structure design. So I think there is a more appealing and I think a more important way that we can use the multi-physics integration or coupling in this kind of SNORM or something. I think the AutoCube or lots of scientists right here are trying to do this, right? And you can use this kind of multi-physical integration to strongly enhance the instrument for near-field optics and the polaritons, and then give us more avenues, to explore the quantum and the superconducting and the topological insulated materials and find some new physics, right? Okay, before I close, I want to express my gratitude, okay? And first and foremost to Professor Qin Dai, and poor Qin just missed so many great talks, okay? And to the great PhD student, Chen Na and Han Cao, and this young lady with me and did the experiment, and this gentleman do the theory part. And at last, I want to say many thanks to our close collaborators, Javier Garcia Abajo and Dimitri Basf and Meng Kun here, and many of others. Thanks a lot. Thanks for your attention.
Thank you very much for this firework of beautiful data and polariton steering, negative refraction, and so on. The talk is open for questions in the back.
Thank you very much for nice results and discussion of it. Can you comment, probably it's a technical question, but I didn't get properly, how you launch polaritons on antenna and also probe focusing or kind of guiding of polaritons? On the slide 17, I guess, there is kind of antenna and also probing of polaritons. Is this different wavelengths you use or how it's implemented? Yeah.
Sorry, can you simplify your question?
How you excite antenna to have propagating polaritons from antenna and also measure polaritons with your tip, as in the sense, no, yeah.
Okay, I think it's the experiment set up like this, right? And you see this is a p polarization electric field as illumination or incident light, right? And this kind of illumination can excite the resonance about this gold antenna, right? To excite some plasmas in this antenna. Also, the antenna can scattering this kind of illumination frequency, and combine this resonance plasma and the scattering light, you can carve a lot of white wave vector, right? This wave vector can cover the dispersion about this polariton. So because the momental conversation, so you can just to excite this kind of polaritons. Hopes a little bit. Thanks.
Yeah. So maybe I have a related question. So since the antenna provides the momentum for launching the polaritons, which role does the tip play? Is it like a metallic tip or a dielectric tip? And how do you exclude tip excitation?
Okay, so this is a good question. It depends, right? And I think, you see, for graphene plasma, it's just like one monolayer. So if the experiment you has antenna and also use the tip, and both of can excite the polaritons, okay? So it's complicated. Yeah. But in our experiment, you see this is a slab about this MO3 structure. It's like a several hundred nanometers thickness, right? So here's the thing is that if the tip is right here and the illumination will also can, there is a hot spot underneath the tip, right? And the tip launches the polariton. But because the fallen polariton is like, to propagate inside these materials, so it can just, to go through about this antenna, right? But if it's the graphene, the antenna will reflect this kind of polariton. So you can see that this can be simplified that the tip launch efficiency, even it's high, but it's not affect this result.